What up, pathways? Data, believe it or not. If it's science, there's a way to prove it wrong. Yes. So this is going to be, we're going to refer to this as the Anivia Harps lesson because she set the stage for all of this and taught me how to teach it. Okay, so step one, hi. Oh, you see my little friend. He's been so busy. Look at that, nice, the magic. We're gonna put that away. And the first thing we're gonna do today, you guys, is up here on the crazy board of magic. Can you see it? It's like that. Least action. So looking at my table, looking at yourself, like how you're sitting there, are you obeying the principle of least action? Is there anything on this table that is not obeying the principle of least action? Like now if you're like Anivia, maybe these are not obeying the principle of least action. But let me ask you this. Are they doing more than they have to do? See, Nivia's like, well, they don't want to be like that. Yeah, but given the fact that I messed with them, for as much as I messed with them, did they do more than I made them do? No. Is this thing right here in my hand doing more than I'm making it do? Is anything ever doing more than it's being forced to do? That's the principle of least action. Well, you got the answer right. Answer, no. All right, so peace out. And then I, quick review, I said that these guys, when I push them, are gonna make noise, but these guys are gonna make more noise. Now, is that a scientific idea? Let me pick this up a little because you can't see my face. Or I can get a little lower. When I push these, are they going to make more noise or less noise? I said they're going to make more noise. Is that a scientific idea? And I think, I'm trying to remember, but I think Anivia was like, yes, that's scientific because they are going to make more noise because we're going to be proved true when they make more noise. That's not the principle I'm teaching you. The principle of least action is not what I'm talking about. How scientific it is what I'm talking about. Do you mind? Hey, just come over here, my little friend. I'm talking about how scientific the idea is. If I say these are going to make more noise, is that a scientific idea? Yeah. But not because it's about to be proven true, but because there's a way to prove it wrong. What? You could push it and they make less noise. Listen. And now listen. If I push those and they make less noise, then I have to admit, I'm wrong. Ready? Ready? Okay. 1, 2. What the? Glued them. I glued them just to be able to mess with you. So I have been proven wrong. My hypothesis was wrong. Yeah, well, because I got tricked. Well, yeah, so what? It still was wrong. That's how you know it was a scientific idea. There was a way. There was a way to prove it wrong. Are we cool? It's not because I will get proven right. It's because there is a way to prove it wrong. That's how we keep each other honest and we keep each other humble. And when we do science together, that's the jam, man. That's the place we want to be. We want to like show up, throw our ideas out there, right or wrong. Anivia was like, she was just so wonderful at that for me yesterday. Thanks again. Shout out to you. So this is the Anivia lesson and principle of least action. Everything is doing the least that it's forced to do. The idea came up also. Anivia and I were talking about the fact that comfort plays into this. I was like, why are you sitting there? She says, because I'm comfortable. And that actually is a pretty good physics principle when you relate it to the physics word of energy. So let me ask you this. How do these relate? If you're getting more and more comfortable, are you going to a higher and higher energy state or a lower and lower energy state? Look at the chairs again. One pile is in a high or low energy state. And Anivia saw, and I think you guys too, this one is the high energy state. Yeah, even with the glue in there, it's still a higher energy state. And it is therefore more comfortable or less comfortable? And we agreed, less. So when comfort goes down, energy go up. So high comfort equals low energy. And I think when Feynman talked about the principle of least action, he said everything goes to the lowest energy state available. So that's like the fancier physics way to talk about it. Everything is getting as comfortable as it can right now. All right, next victim. Ready? Whoosh. You know it. You love it. Garbage over there coming at you. The next part of the physics lesson, the reason you showed up today, the exciting idea. Wait, how about a little musical background? How about it? Nice. So the question is, oops. The question is for you to consider. And I'll let you think about it as you listen to the cool science music. I think you get the point. Is that a big monkey? And most people learn the second part of the question as a matter of course when you're with me. And you'll be with me like a year from now, and you'll say something to me like, oh, but Mr. Kelly, this is big this. And I'll say, oh, that's a big whatever. And you'll be like, yeah. You'll be in a dice quiz with me, and I'll say, is that a big monkey? And then hopefully it'll click, and you will say to me, whoosh, compared to what? Compared to what? Is that a big monkey? Well, compared to something, it probably is kind of a big monkey. And compared to something else, he's probably not such a big monkey. And then one year I had this kid. He was really smart, but he was sassy. And I was like, okay, because his brother was in the class, and I was like, hey, is this a big monkey? And he was like, which one? And I was like, that's not supposed to be asked. And I was like, what do you mean which one? He's like, that one or the one holding him? He was calling me a bad thing. No, it's not a bad thing. Monkey, I think maybe would be cool. So he's small compared to this monkey. He's maybe big compared to this monkey. But now another question enters the game, you guys. What do I mean by big? Because there's different ways things can be big. And I came up with my list of bigness. Take some notes, but I was like, it's all good. I will post these notes for you too, if you want. I can just post the list of the notes or put it in a slideshow if you want. It's all good. So first bigness I want to talk about is tallness. How are we going to talk about the tallness? Okay, there we go. All right, so now, the tallness of him. Is this a tall monkey? Well, let's say compared to this monkey. Or let's do another sitting down monkey. I got this one who sits down. So, sitting there, who's taller? Well, him compared to him, he'd be taller. Cool? I think I could ask wideness right away. Who's wider? And you'd say, well, he's wider. Well, how do you know? Well, look. He can block out the sun from him, but he can't from him. So he's gonna be wider. Actually, blocking out the sun is more of like a tallness combined with wideness, isn't it? That's like the area that they cut out, the size of the area they cut out. All right, so what I've done so far when I've compared these things is to qualitatively compare them. I'm basically saying bigger, smaller, smaller, bigger. It's not numerical. I haven't put numbers into the game yet. So that is something you got to know for your test and for your field journal, you guys. A qualitative description or measurement. I don't know if you measure really, but qualitative means no numbers, basically. A no numbers comparison. We'd say bigger than, taller than, wider than, etc., etc., etc. Are we good? Yay. All right, so now, what if I wanted to get quantitative? Let's put that up here right away too. And I think you guys see where it's going, and the word's kind of right in there, right? Quantity, quantitative. This should maybe turn a little bit. Yeah, hi. Hi. Quantitative. Quantitative. So now there are numbers involved in the comparison. Numbers do the comparing. So now we want to get quantitative, Quantitative. Okay, good enough. Quantitative version of that. Now we got to get some like measurements in. And we're going to do that right here. So I've got the fancy stick right here. And Mia and Anivia had fun with this, and she knew right away, well, not really right away, but when I held it up like this, I was like, hey, Anivia, what's that? She's like, oh, it's like a big stick. And I'm like, what kind of stick? And he was like, a meter stick. I didn't have to tell her that word. She knew it right away. Yay, so this is a meter stick, and it's kind of broken into like this. Do you see where I broke it into 10 pieces? And then I broke it into 100 pieces. And then I took out of my pocket a penny, because a penny is how much of a dollar? It's 1 cent of a dollar. Guess what this is? 1 cent of a meter. Can you dig it? Cent of a meter? 1/100th of a meter? I'm sorry if this is like pedantic or talking down to some people, like, oh, like some people are like, duh. But then I just want to reiterate that other thing. Well, some people aren't, and we should never be. Well, I never knew that. Well, then it's cool. It's all good, right? We're all dumb, just about different stuff. Yay. So now, just for measurement purposes, I'm going to go like this, and I'm going to say, hey, how tall is this monkey? And I got to tip it back a little. And I think you'll see, sitting there, how tall is he? Interesting. Do you see that he's taller than the 20 with his hat on? The hat comes into play at some point too. But with the hat on, we'll give him the hat. He's taller than 20, but he's shorter than 30. And if we come over to his little friend from Valpo, this was from Genevieve. Another former student gave me this one. Genevieve gave me that one. She went to Valpo. How tall is he sitting there? Oh my gosh. Almost. He's just a little more than the 10. Or the 1, I'm sorry, it's 10 on this side, right? Because it's 10 centimeters. But he's taller than the 1, and he's shorter than the 2. And this little person is taller than the 20, but shorter than, or taller than the 2, but shorter than the 3. So what do you say? And now this is really important for our lab, you guys, because we're going to be working with these guys in the lab. These guys, and you maybe know what those are. That's called a graduated cylinder. We're going to be measuring liquids in that. And sometimes that liquid line is going to come like in between the two things. And what do you do when you see that? Well, this is what you got to do. You basically gotta Johnny eyeball it, I call it, and you kind of like you say how you put a number on it. And I think if I'm not mistaken, Anivia's number was 2.2. When she looked at it, she was saying, "Hey, I think that's like 2.2. That's how tall he is." Cool. If I flipped it around, do you know what it would be? 22. And it really is close to 22. But if I'm on this side, you guys, it would have said 2.2. On this side, maybe I'd have to say 22 point something. You follow me? If it's in the middle of two lines, you get to estimate that thing. So that's important when you set you up for your lab. Because when we're doing the lab, you guys, I'm just going to zoom in. I'm not going to say, put this number in your notebook. You're going to have to put that number. You don't have to read it yourself. Cool, cool? Cool, cool. I forget I got to look my cameras over here. Otherwise, it looks like I'm looking in crazy land. Sorry, you guys. All right. So this little guy went, and I'm going to get my eyeball down here, which is the other thing you should do. Get your eyeball right down there. All right, sorry guys. He's totally taller than the one. And for me, he's like, I'm going to say 10.5. Looking at this side over here. You guys might say 10.5 would be centimeters. These guys are like decimeters. So not really a word you're going to have to know too much. But it's like a dime's worth of a meter. More accurate, but given your scale, you're fine. You always make the best estimate you can. And the other thing I talked about with Aniva was like in the real hardcore science world, like when measurement is critical, you will say plus or minus numbers with your measurements. So you will tell the person who's looking at your measurements how good you think that measurement is by putting a plus or minus number on it. Cool. For our lab, we're not going to be dealing with that, where the precision or the plus or minus is going to be a big factor, but there might be a lab in data, believe it or not, or a thing Miss Mary or Dr. Knetter wants you to do that's going to require that. So be ready for it. Okay, tallness, wideness, thickness, like how deep are they? We can go this dimension, how tall, how wide, dope. And then we can go how like thick or deep. Yay. Yeah, we can go tall, wide, and thickness, and those are 3 dimensions. And now we're going to talk about combining units. All right, so now we're going to talk about like combined units. Like if I drew his outline on here, yay, and then I drew your outline on here. Let's do it like this. Yeah, let's do it like this. He's not a great drawer, that Mr. Kaler. And call me Steve if you want. I don't care. It's all good. He's not a great drawer. But we talked about like tallness combined with wideness, and tallness combined with wideness. And I think you guys know what we're talking about. Maybe tallness, some people would call it length. Like how long is he and how long is she or whatever. Are you digging this? And I think you guys know that tallness combined with wideness is the same as length combined with width. And that tells us a different thing about like how big they are, and that's that area is the fancy word for that. So is this a big monkey in terms of area? Well, compared to what? Compared to this monkey? Yeah. I think so. And some people would maybe even count the squares in there. I don't know if you guys can see, I got little squares on there. But whatever, you could like make a measurement of length and a measurement of width and then turn it out. If it's a perfect square, it's easy. Or if it's like weird circles, it's hard. Sometimes you got to average, and then maybe your plus or minus number changes. Is he have a big area compared to this monkey? It doesn't even takes the whole thing. Yay. All right. So compared to him, no. Compared to him, yes. We're good. We're covering our bases. Who does he have a big fur coat? Does this monkey have a big fur coat? Well, compared to this one? No. Compared to a littler monkey? Maybe. Yep. That's called surface area, and that's kind of tricky to do on a monkey, but I don't got like a formula for that, but I'm guessing there's probably a way to do it. You could take it off and lay it down, right? It sounds mean, but he's just stuffed, I'm just saying. But if you took the fur off and laid it out, you could get like a measurement of that. Surface area. Heaviness. Is this a heavy monkey? Oh no, volume first, you guys. Volume. How about this? Is this a big monkey? In terms of volume, does it have more volume than this monkey? And maybe you're thinking, yeah, but then I gotta show you this. No thickness whatsoever. Well, there's some, because it's like cardstock. But you get it, right? Tallness times wideness times thickness. Oh, you're gonna win that one, right? Coolio. So volume is all 3 times each other. Let's get that on the board right away. So that's like if you're looking at like something that's cubic, right? I remember how to do that. Yes. So now I've got like the length going up, and I got the width going sideways, and then I have the thickness or the depth, right? And if I go length times width times thickness or depth, that's what turns me into volume. Cool? And there's a formula for that, but it's kind of just like another way to talk about bigness. Like, how much space do you take up? How much space, how much sun do you block out? How much, yeah, you get it? And these again are quantitative. Why? Because I'm putting numbers in there. I'm gonna make measurements of length times width times thickness and get a number for volume. Note to self, this is gonna come out in centimeters times centimeters times centimeters times centimeters times centimeters, which comes out in centimeters to the 3rd power. Up here, I got centimeters times centimeters, which comes out to centimeters to the 2nd power. Centimeters squared, that's the units, yeah? For area. Units and units. Are we cool? I think we're good. Okay, last couple things to talk about in terms of compared to what monkeyness. Is this a heavy monkey? Does he have a lot of mass? Now those 2 things are different, but for right now, I'm just gonna basically mush them together. But does this monkey have a lot of weight? Is this a heavy monkey? And you're looking at me saying, yeah, I can hear it. Compared to what? I can hear you compared to this monkey. And you're going, oh, yeah. All right, so now, is that a scientific idea? Is there a way to prove it wrong? It just so happens there would be a way to prove it wrong. And it looked like this. So nothing up my sleeve. I just got like the nice little scaly rama. And I'm gonna put him on there. And if my idea that he's a heavy monkey compared to this monkey is wrong, when I put this on there, what's gonna happen? And then you said he's gonna just stay down there. This guy gonna stay down there. And then I went like this. He's all full of crazy tricks. Yeah, this one, after Genevieve gave him to me, I like put a hole in there and I dumped BBs in there. Just to prove a point. Yeah, just to teach an idea, right? So you get the idea. He's full of BBs. But don't miss the other point. Was this a scientific idea? Yeah. Because it was true? No. Because there was a way to prove it wrong. And in fact, like before with my glued chairs, this is heavier. So, how do we talk about bigness? It depends, right? Is it bigger in terms of weight? He's bigger, heavier. And now we come into our thing, which the lab is going to talk about. I got a few more points to talk about, but I'm going to mix them in there because we're right at the point now where I want to talk about another way to discuss the bigness of the monkey, and it's how squished together stuff is. How smushed together or squished together stuff is. And the fancy word for that in physics is the thing your lab is all about. It's the name on the thing you clicked to come and watch this video, I think. It's density. That's the fancy word for how smushed together stuff is. Cool? So this is bigger in terms of volume, but smaller in terms of mass. Bigger in terms of mass, smaller in terms of volume. There's more stuff like squished in here than squished in here. So we say high density, low density. Cool? That's the qualitative version. Quantitatively, well, we're going to have to get some numbers here to do that. In our lab, we're going to get numbers by putting the liquid on a scale, measuring how much mass it's got and how much liquid it's got. And we take data points to do that. Coolio? Coolio. All right, so now I want to talk about density a little bit. I'll give you just a couple notes on that. Are we good? We're good. So maths was in the video, and I was sitting with Mr. Chair, and I was like, maths? And he's like, yeah, that's what everybody all over the world except us says all the time. And I'm like, oh, well, I was dumb about that. Yes. But in any case, there was one thing he said that I didn't really like the maths guy, and it was just, he said something about if it's proved wrong in the laboratory, we reject it, the idea. But if it's proved right in the laboratory, then we accept it. And I was like, wait, we accept it with conditions, right? We accept it with, it hasn't been proven wrong yet. The evidence seems to support the idea. That's what we say. If we're being careful and we're being honest and we're being humble, that's what we say. That's the scientific pursuit. But now, so now we're going to talk about the maths that we got to do for density to get you ready for the lab. Because there's a little bit of math in there, you guys. And it looks like this. Now we're going to talk density. First of all, first note, maths are invented to explain physics. Don't get freaked out. Don't be scared. Physics usually, like once you get your ideas, like how squished together it is, the math of this is going to like, oh, duh, I get it. And then if you're lost by this one, when I get to the Cheetos, which again, this was sparked by my lovely lesson with Anivia, she like woke up this idea, like something, it wasn't relating, I couldn't get it home. So I got the Cheetos and I think that's gonna do it. But let's do this one first because it's in the notes this way. The first thing we're gonna deal with is the picture of how squished together stuff is, mathematically speaking. Cool? And you see there the thing, I'm just gonna write it big. Density is equal to m over v. Now, above that, in the previous thing, I talked about density as equal to how squished together the stuff is. I just want to point this out to you. These marks that I had to put on here to communicate that to you, or all the words I had to speak to communicate to you, look at all of those marks I had to make. Density equals m divided by v, where this is mass and this is volume. If you know how much mass per volume there is, and the division sign, in my world, for me, if you can draw them this way, it's always better than the slash way. Like m per v, I don't like that. It goofs people up. It makes people think that they're next to each other when they're on top of each other. It's a fraction, you guys. This is a fraction. Cool? We'll talk more about the fractional nature of it in a minute. I use 1, 2, 3, 4, 5. Well, if you count the equals, then 6. But 5 marks to communicate the same idea? Yes. Nice, because if you take the mass and divide it by the volume, you'll have a measurement of the mass per volume. How much stuff per space. That is what density is. It's like how squished it is. And that's the quantitative way to numerically put it together. Can you dig what I'm trying to sell here? Yeah, all right. It's cool. Oh, one more thing. Actually, 2 more things about density. My former student of mine, I'm sorry, that's how old I am. I'm kind of nostalgic because I'm an old man. She taught me to do it like this. She was a former student, and then she became a teacher. She was like Angela Vicchio is her name. She works now out at the park by Summerfest, the state park out there. She's their like science person. She kind of runs that show. She's great. But she taught me this, and I think she might have bit it from somebody, but she said density is love. Get it? Because it's like the heart with the cross, but it's the M and the V. Cute. Help make it more memorable. And then one more thing that I'll do with every 3-player equation, I'm going to do it like this. Cool? So if this is going to be in units, density is going to be, oh, did I tell you this? It's going to be in units of grams per cubic centimeter. You okay with that? The mass is going to be in grams. The volume is going to be in centimeters to the 3rd power, and then this is going to be in grams per cubic centimeter. Yay? Okay, so now the beauty of this, and maybe you've seen them before again, if it's old news to you, then ignore me for a second or skip ahead in the thing. But the beauty of this, I was working with Anivia, and it's like, this is the pyramid of algebraic power. So if you cover the one you want, the formula is what is left. I'll even write that for you. Cover what you want to find out, like in the math problem on the story problem in the Alex or whatever it is. They'll say the density, or what is the density of something, blah, 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 with this much mass and this much volume. Well, the formula, if I want to know density, is right there. Well, it's the one we already know. You get it? Cover the D, and D is going to equal M over V. Woohoo! But here's where it's cool. A lot of people can do this algebra, like their algebra is really sound and they can just rearrange them. But if you're not great at that, this is your friend. What if they say, what will the mass be? You see what I did? Cover the M. And then I'll say, the formula is the stuff that's left. So the formula for mass is, what's the stuff that's left? D and V, but they're next to each other, so that means they're timesed. Yeah, you multiply. Yep, so M is going to equal D times V, and the dot or an X, I hope you've seen that notation. They're both just same ways to say, different ways to say the word times. And if you want to know what V or the volume is, look what's left, you guys. V is going to be M divided by D in the calculator. Every one of them like automatic, and you don't have to like rack your brain too much. Just cover it up. Oh, M over D. Oh, D times V. Oh, M over V. Bam! Next victim. Density as a fraction. I've only got, what? I think I got like 3 more pages, you guys. And then we'll be in lab land. And it looks backward to me, which is a discussion that's interesting to have some another day. The mirror image thing. I use that in my acting class all the time. You don't look like what you think you look like. It's true. You think you look like the flip of yourself, because we're all used to mirrors. Anyway, blah, blah, blah. So that's what I'll deal with quick. Let's take him down. Every fraction asks a reasonable question, friends. And I remember I was learning how to teach, and I don't remember what the teacher was who taught me this, who said that to me, but I was like, it really rang a bell for me. It really like opened up a bell to me when I realized this right here blew my mind. It's asking me a question and telling me the answer at the same time. It's asking me, how big is the top thing? What's the top thing? 1. Compared to what? Compared to the bottom thing. 2. Well, how big is 1 compared to 2? Half as big. It presents the question and answers it at the same time. And I was like, phew, kind of blew my mind. But every fraction is just asking you a question, man. How big is the top thing compared to what? Compared to the bottom thing. Yay? Yay! All right, so now, so now I got a few examples. I got the one that's obviously in front of us. Density is the answer to the question, how big is the thing's mass compared to the thing's volume? I suppose I could do this, you guys. Let's get crazy, kids. You crazy kids. Here we go. I'm going to get crazy, and I'm going to find his mass right now. Shall we? Shall we? Oh, wait, do I have the electronic? Yay, I have an electronic scale. I can just set him on there. That'll be easier. That'll be a little easier than sliding those crazy things around. All right, you get on there. And I got 200. You guys see that? Can you see that? 200. I think you can. It is 296. And now I'm going to say the ballpark measurements for the length, width, and height are going to be, ready? I said about 20 by about 20 by about, well, he's a little taller than 20, but he was a little not as thick as 20. So I'm going to just round those off. Okay, guys, forgive me, just so I can do quick math. KK? KK? The density of monkey is the mass of monkey compared to what? The volume of monkey. All right. Oh, monkette. Right. All right. So mass of monkey, that one was easy. We just read that off the scale. And it was, I forgot already. 297. 297. 297 grams per 20, let's do it down here, volume. Let's do it as a separate thing. 20 centimeters times 20 centimeters times 20 centimeters. 2 times 2 is 4, 4 times 2 is 8. 8. 1, 2, 3 zeros. 8,000 centimeters cubed. Nice. Didn't even need a calculator. Woo-hoo. No shame if you did. Who cares, right? I don't care. 8,000 centimeters cubed. 297 divided by 8,000. Gonna need a calculator for that one though, crazy kids. Unless you got one, just yell it through the void to me. I can't hear you. I'm all alone. 297 divided by 8,000 equal 0.037125. 0.037125. Does that sound like a reasonable number? And I love to ask myself that every time I get the calculator out. Because a lot of times people can do crazy things. They just think whatever that thing says to them is right. And I'm looking at this, and I got a smaller over a bigger, so this should be less than 1, it says to me. And is this thing in my calculator less than 1? Mm-hmm. If it had said something more than 1, then I'm going to go, whoa, crazy, right? I got to re-push the numbers in. And just for fun, and since I can do it in front of you, I am going to do it in front of you. You can see if I goof something up, right? I need it on the gimbal because I'm going to do that for the data later. You guys, that's why I got it on the gimbal right now. 297 divided by 8,000 equal, yeah. I got the same number twice. I'm happy with that. Now, there's a trick in the math world, in the science world, where you look at what are called significant figures. Because some people will write all of those numbers. Well, you can't know that many numbers if you didn't put in that many known values. Like you're saying this is like 1, 10, 100,000, 10,000, 100,000, millionth. Like this 5 right there, you guys, that's like a millionth of something. Well, you didn't measure nothing to a millionth of anything. How can you give me an answer that's in millionths of something? So rounding is kind of there's a process for that, and we'll talk about that. I'm pretty sure we will at some point. Talking about like how do you use significant figures to round things off, like how far should I round it. For this, I'm going to give you just a real down and dirty rule. If I've got 3 significant figures here, this is really technically 1 significant figure here. I'm just going to pretend like that they're both 3, and I'm going to round off to 3, and I'm going to say 0.0371, 0.0371 grams per cubic centimeter. That is the density, the approximate density of monkey. This monkey. Yay. Other monkey, different density, bigger density. Should we do it? We should do it just real quick. What's his volume going to be? Well, let's measure. Measure. Real quick, down and dirty. He is, I'm going to say, put your arms in. Come on. Be more like a cube. I'm going to say, oh, put it in front, dummy. I'm going to say 10-ish. He's like 10 wide. And I'm going to say, we know he's about 10 tall. And I'm going to say, yeah, about 10 thick, you guys. That's not too shabby. We can say that. That'll be easy then, right? 10 times 10 times 10. And he's so heavy, I wonder if this thing is even going to measure him. He's such a big boy. He's a heavy. Yay! 795. Hooty hoot. So for little monkey, let's do him in red. Brown, I don't got it brown. Density of little monkey is 795 grams over 10 times 10 times 10, right? 10 centimeters times 10 centimeters times 10 centimeters. That's all approximate, right? And that comes out to 795 over 1 times 1 times 1, and then 3 zeros. So that's 1,000 centimeters cubed. And calculator says, calculator says clear. 795 divide by 1 bump. Oh, some people are like, Mr. Kaler, why'd you get a calculator for that one? All you got to do is move the decimal over 3 places, because you're dividing by 1,000. So you're just going to go ha-ching, ha-ching, ha-ching. Some people know that. Some people don't. Some people do. But it turns out 0.795 grams per cubic centimeter. Now let me ask you this. Is this more money or less money than this much money? And the whole crowd of data believe it or noters said, would you rather have a little more than 3 cents of money, or would you rather have almost 80 cents of money? Well, duh, dude, give me the 80 cents of money. Yay? Yay. That's more density than that. You can tell because the number's bigger. Coolio? Coolio. Next victim is unit price. Unit price is the answer to the question, which bag of Cheetos is economically best to buy? So I was racking my brain, what do kids go buy that they would care about, that would relate to, that'd be able to relate to? And it's like, oh, Cheetos. But they liked Flamin' Hots at my school more. But I couldn't find a little bag of Flamin' Hots. They had the big one, but not the little one. So I got the regular Cheetos. So, there it is. And my cost here, you guys, there I did an advertisement for that store. The big bag was $3.49 and the little bag was $1.89. So now, unit price is the answer to the question, which is the smarter buy? Unit price. Unit price is a great, compared to what? It's often a little sticker at the grocery store. There'll be a little sticker underneath the different size bags, and they'll say unit price. So they did the work for you? Yeah. And you're like, oh, well, we're only paying this. This is a better deal. Why? How did you know that? Well, look at the unit price. What do you mean the unit price? Well, it's not just about how much money you're spending. It's about how much money you're spending per Cheeto. Compared to what? Compared to the amount of Cheetos I get. Yay? Ringing a bell? I hope so. I'm so excited. I'm going to switch to the markers because I came up, well, hopefully with something you guys can relate to. Hopefully. All right, so it goes like this. I got a little bag, and then I got big bag. All right, so now we're going to talk about cost per Cheeto. I don't want to know the cost. I want to know the cost per Cheeto, man. Tell me about the cost per Cheeto. Now we got to do a little bit of math in here because it says 21 pieces is a serving. Can you dig it? And there's how many servings per bag? Ha ha ha. I can't read backwards, so I got to look. 9. 9 servings times 21 pieces. So 9 times 21 should be how many, right? This is in the big bag. The cost, we already know. Cost for the big bag was $3.49. And now, for the number of Cheetos, how many Cheetos is that? Well, that's going to be 9 times, what'd they say per serving? 21. 9 times 21. So let's do that. Clear. 9 times 21 equal 189. So I got this. The money is $3.49 per 189 Cheetos. What's the cost per Cheeto? Well, I can do a trick. If I turn my calculator sideways, I can turn it sideways and I can push the 1 over button. But I won't do that to you because that'll mess with your brain. But it is easier that way. So I'm going to take it, I'm going to do it from scratch. $3.49 divided by 189 Cheetos, 1.0184. And again, I'm just going to round it to 3, which is going to be 0.0185. So this is equal to 0.0185, right? And this is dollars per Cheeto. Now, how much money is that, friends? How much money is that? Well, it's like a little over a penny. You'd say it's like almost, if I round it up, I would say it's 1.9 cents per Cheeto. Can you dig that? Now let's do this one. You already know what's going to come out. Bigger, smaller, don't you? Is that a good value on them Cheetos? Is that economical? Compared to what? Compared to that? How do you know? How could you prove me wrong? Do the math, man. Get quantitative. Here we go. How much per bag? Where's my calculator? $1.89, friends. $1.89 divided by how many Cheetos in there? 21 pieces per servings times 3.5 servings. Come on. We're killing time. Clear. I got 3.5 servings, and every serving has 21 Cheetos in it. So I got 73.5 Cheetos in that bag. Coolio, 73.5 Cheetos. So now, how much money per Cheeto? Let's find out. $1.89 divided by 73.5 equal 0.0257. 0.0257 dollars per Cheeto. And I'm going to just tell you what that is, but maybe you can see it. This is going to round off to like 2.6 cents per Cheeto. Look at that. Which is economical? This one. Well, you probably knew that already, but do you see how the math is like your friend? It just kind of makes sense out of stuff and like saves you money, helps you be smarter buyer sometime. Once in a while, you'll see, I'm telling you, paper towels are like this. Like you think you get the monster pack of paper towels, you're getting a deal. I've sat at the Woodman's with my calculator in the paper towel aisle. It don't work like that, man. The per sheet or per roll, it's not always the big one that's the best deal. In fact, very often, it's not the biggest one that's the best deal. So, there you go. Unit pricing, hopefully you can relate to that in terms of money. And I'm going to move on with the lesson. Kwa-ching! How you doing? We're almost at what I'd like to say is our time. I was going to talk about speed and start graphing, stuff like that, but just because we're coming up on an hour, I want to wrap this up. So, we're going to cut to the chase. And the chase is, yeah, I'm going to cut that. We're going to go into my next note session, and I'm just going to prep you for the lab and not keep you for more than an hour. God bless Anivia, because she was like hung out with me for like an hour and a half. So I'm going to talk about the lab right now. We're going to be measuring the density of 4 liquids, ladies and gentlemen. We're going to compare and contrast them, and we're going to graph them, and Miss Mary's going to teach us how to do that in the cool program. But when you put on a graph, you guys, and I'll just show you real quick. Graphing is like your friend when it comes to trying to see what's going on. Graphing is your friend when it comes to seeing stuff. Like if you graph, and I was going to teach you this, but I'm just going to really quick. Like if this is the miles and this is the hours of time, you can see how fast a car is. I can show you 2 cars. I'm going to show you the black car, and I'm going to show you the red car. And real quick, do you know which car's faster? See, fastness is not just about miles. It's not just about hours. It's about miles per hour. So where do you look to see miles per hour? I wonder if you guys know that the black car is faster. But wait, the red car went more miles. Yeah, but it took way more hours to go those way more miles. So this has to do with the way the ratio gets played out. Can you dig it? If the top of the fraction gets bigger, but the bottom of the fraction gets more bigger, then the ratio of the fraction gets smaller. Can you handle that? We're going to have much more to say about this, and I might do an extra video, but just for the density video, we've had enough. We got compared to what? I got the Cheetos in there. But in the world of graphing density, you're going to be doing not miles per hour and looking for how fast. You're going to be looking at, oh, this is maybe interesting. Maybe you guys can see this. Speed or velocity, I'll write speed, is equal to miles over hours. Do you see? It's just kind of like this, you guys. I'll give you one more hint. Rise over run. Sounds like a math class. Kinda. Maths are the language of physics, you guys. Rise over run. Miles over hours. Rise per run. Miles per hour. Slope helps you see the speed when you graph it like that. Yay? Like this many hours, this many miles. This many hours, this many miles. This many hours, this many. You graph it out and you can picture the speed. Similarly, if you graph out the masses and the volumes, I'll write those words. Yeah, you can see the density when you graph